The reason why we put this Saturday lecture is because I had a couple of meetings Monday and Tuesday, grant meetings, and if I don't go there, somebody else will take my grants. This is very competitive, and the sponsors wanted to investigator to be there. So I had could take the flight on Wednesday, and then I arrived Friday. So Utpal moved me to Sunday and not Sunday, right? The rest of the lectures were put in distributed high. Oh no, I don't need a mic.
Actually, we are recording.
Oh.
We are recording every lecture.
Yeah. Oops. So now that will settle it. No? Must have dropped coffee in here. Okay, so now I have to be careful about what I say. And the purpose of these preliminary lectures is to maybe bring people up to speed in some of the basic subject areas in which we are going to have this discussion in the next 2 weeks. So as you may have noticed, the theme of the workshop is stochastic analysis, and apologize for this mark because I just spilled tea. Is looking at stochastic analytic aspects of fluid mechanics and also control theoretic aspects of fluid mechanics. Both in some sense are very old subjects. You could say the probabilistic ideas of fluid mechanics goes back as at least to Osborne Reynolds in the late 1800s. 1893 he wrote famous articles. These days routinely fluid mechanics talk about a concept of Reynolds number, which we will define when we go on. And that paper, if we go and look at in Philosophical Transactions of the Royal Society in 1893, he takes various averages and talks about equilibrium, global equilibrium, and so forth. So it's the statistical viewpoint for fluid mechanics is well over 100 years. Control theory and control ideas for fluid mechanics is probably even older. If you maybe surf the YouTube, you may find the history of aviation, history of aerodynamics and flight, human flight, and then you will find that before Wright brothers, there were all kind of failed attempts to fly, and that goes to Leonardo da Vinci. Even pictures of various, helicopters and various flights. So every time you talk about flying, the notion of control is there. You want to stabilize your some configuration, and then you want to control. So what is new is maybe bringing these concepts in the modern viewpoint, in the bringing bona fide control theory and bona fide stochastic calculus into equations of fluid mechanics. I didn't learn it this way. I sort of trained originally as my undergraduate was mechanical engineering, so learned a lot of fluid mechanics, heat transfer and things like that, fluid mechanics, and then masters in. So when I went, so that was in Sri Lanka, and then when I went to US, my single purpose was to learn high-speed aerodynamics, because I didn't study high-speed aerodynamics, and I didn't study, then I want to, and then of course, after masters I went to applied math in another institution. So at that time these subjects were not brought together, they were different disciplines, and probability was a total mystery to me at that time. Control theory I studied separately, fluid mechanics. But now we can actually combine all three, and that makes it interesting. But of course I want to, now that the subject is fairly at the sort of well solidified, we can ask difficult questions, maybe we can ask more practical questions, more physically oriented questions, depending on your test. The purpose of this meeting, I hope, is to stimulate the next generation to start thinking about this subject and ask tough questions depending on your taste and background and opportunities, and develop it further. So I want to first set the stage just to tell you that similar mathematical ideas also apply to other disciplines, very closely related disciplines mathematically. And then we will spend, of course, I will spend most of the time next week and week after talking about the things in which I have published, but I also may touch here and there the topics I want to mention today. So, as you may recall, the Bardiyar students, how many, can you raise the hand? All 9 are here? They all at that corner. You know, I told Professor Balachandran, head of the department specifically, that make sure that you also send female students here. And I was pleased to see Bardiyar, who advocated. I would be very proud. Anyway, so so in the Coimbatore lecture, we spoke about not just fluid mechanics, but also we spoke about more focusing on general relativity, because it's and then spoke about fluid mechanics as more as a special subset of that viewpoint is a legitimate one, because control and stochastic ideas, I think, not only these, of course, variational calculus and functional analysis have already been very big in these traditional physics disciplines, but control and stochastic analysis will also have opportunities in what's called contemporary physics, standing from the fluid mechanics viewpoint. So I want to first spend maybe 20-30 minutes talking about not just fluid mechanics, but in a broader picture, because as a defense scientist, I am exposed to not just fluid mechanics, but I am also not only exposed to, but often called upon to deal with problems in electromagnetics or sometimes in quantum physics, in which I have never had training. I had to teach myself. Okay, so we want to essentially talk about control and stochastic analysis of fluid mechanics. That is the main theme of these lectures, but we will say of physics. Where did I? And then we will specialize, and I will tell you how the fluid mechanics fits in here, and also we in this way, it will give you an opportunity to embed your thoughts into some of the mainstream developments today. Navier-Stokes equation is not the only thing that is in the mind of the top PDE theorists, right? They are also thinking about Einstein field equation. They are thinking about the Dirac equation. They are thinking about the Boltzmann equation. The latest Fields medal by Villani, Cedric Villani, is for the Boltzmann equation. So where do these things fit in the, and is it a very, of course, I haven't developed control theory and stochastic analysis in all these other fields, but we will, at least I will show you first, just briefly discuss where these subjects fit in, and then we will take off and discuss fluid mechanics mostly. And in that way, if you say that, okay, maybe you don't want to work on fluid mechanics, but you want to work on relativistic quantum physics or something, this would have been some of help. Okay, so first of all, we call it non-relativistic. So in this non-relativistic setting, maybe at least I will talk a little bit about the Boltzmann equation. May not start here, but the Boltzmann equation, and and then there's also a natural counterpart with the Boltzmann equation plus the Maxwell equation. So here you know this the type of equation is for statistical dynamics of just individual particles. When you first learn classical mechanics, the Newtonian mechanics, and then immediately go and study fluid mechanics, then it looks like how did this come from? But that's how we are going to start our math lecture today, but it looks like completely disconnected. If you start somehow, if you instead of going from classical mechanics, Boltzmann, and then derive Navier-Stokes in a statistical viewpoint, that looks actually more natural, interestingly. This combination of Navier-Stokes, the Boltzmann coupled with the equations of magnetic field is called the Maxwell's lasso in the literature. So the way we the two viewpoint I want to show, this is of course I am just mentioning, is that we will show you how to derive the Navier-Stokes equation. Either compressible or incompressible. Starting from Boltzmann equation. So that derivation I will show maybe during the week. Right now we will, once I finish the general sketch of the big picture, we will go and start with the classical fluid mechanics derivation. But there are a couple of good books where this derivation is given. And I wanted to, since this is a tutorial lecture, I want to give two references in order for you to learn. So the reference number one, to understand the derivation of Navier-Stokes, is a book by Marvin Schinbrot. It's not a new. It's called Lectures on Mechanics. So this is an old book. This is probably 1973 or something like that. 1973. So I'll tell you a little bit about this book. What is unique about this book in the fluid mechanics literature? You have the textbooks in fluid mechanics can be very old. Like a book by Horace Lamb is written actually in the turn of 18th century. 19th century. So 1890 something like that, the first edition. And the bachelor fluid mechanics book, for example, is an old one. The modern books don't say, as far as classical fluid mechanics is concerned. What is classical fluid mechanics? We will see. It is all in Lamb and Bachelor's level, incompressible flow. Schinbrot is unique because first he gives the statistical mechanical derivation of the Navier-Stokes equation. So that is unique in this book. And then he goes and talks about like a regular fluid mechanics. If you go take a course in fluid mechanics in engineering department, they teach special solutions, what they call exact solutions of the Navier-Stokes equation. That's That's what usually either viscous or inviscid setting. So that's what occupies the traditional fluid mechanics course, and so he covers that. And then the last third, he says, is it says a touch of a taste of modern theory, a taste of modern theory, as he called. And so the taste of modern theory, he deals with, that's the type, that's the rigorous Navier-Stokes theory, existence and uniqueness, solvabilities and strong solutions and weak solutions. So this one book brings all this in a very accessible way. As in some sense, there is no other book written like this, which if you have otherwise classical books or modern books like Lerzenskaya, Temam, which only deals with existence and uniqueness type, and then classical books which don't talk about, and then this one is sort of creates a good bridge in between. So this is a good reference to understand how the Navier-Stokes equation is derived. We will derive following a little bit on Shinbrot and a little bit on this other book. I need Barbara's help to pronounce the name. This is Professor Barbara Rudiger. And Chichi Nyani. So the reference to is Carlo Cercignani, Cicciani, right? And the title of the book is The Boltzmann Equation. And its applications. So this is, I think, 1988 or something like that. Okay, so that derivation we will see. It is interesting now that the subject of control of fluids and stochastic analysis is in, like I said, reasonably solidified. Now it is better to back up a little bit and they understand some of the fundamentals so that we understand what kind of questions to ask, right? Not just always run to Continuum Navier-Stokes and prove some theorems. You just want to ask what is the right question to ask. And fluid mechanics is not always water. Fluid mechanics is also can be rarefied fluid mechanics. For example, a re-entry vehicle, when the rockets, when they launch and then when they come back, and they re-enter, they actually enter the what's called an ionosphere, extremely rarefied ionized gas. And incompressible Navier-Stokes doesn't apply that situation. It's more plasma. So it is, and therefore, when you want to understand the dynamics of a re-entry vehicle as it's entering the upper atmosphere, all the way to the troposphere and to the lower atmosphere, it actually goes through different regimes of fluid mechanics, and it's not just a Navier-Stokes equation. So I hope you didn't come with the impression that we are just going to spend all the time talking about hard aspects of Navier-Stokes, but that doesn't mean we will not. Okay, the third reference is probably everybody know is. Okay, so before coming to that book, let me follow what I want to say. So this is non-relativistic, and so now for the modern theory of Navier-Stokes, so this has classical and modern theory. And strictly modern theory of Navier-Stokes, incompressible. Usually it's better to say incompressible flows because you actually mean flow. For a long time, the reference was by Lerzenskaya. We will talk about Lerzenskaya at some point. I just give you a standard reference you all probably know. It is by Roger Timam. He has a couple of books. The book I pick because it's a very quickly gives the entire picture in some sense. It's called the Navier-Stokes equation. And nonlinear functional analysis is CBMS series. So this book is well known. Although it says nonlinear functional analysis, I think probably that's just one result by Kirchner about steady state Navier-Stokes and its bifurcation, where he actually uses nonlinear function analysis, degree theory and things like that. Otherwise, it's mostly linear function analysis. Most of the PDE theory relies on linear function analysis. The nonlinear function analysis, there aren't too many methods that commonly used. These monotone operators, accretive operators, those are more common. And then there is degree theory. Beyond that, there is things like mountain pass lemmas and sophisticated theorems in non-convex analysis, non-smooth analysis, which are occasionally used here and there. So, but this is, I just wanted to give some standard reference so that we sort of say that what are the boundary conditions of our discussion. So I wanted to call your attention to the fact that we need to go back and see how this comes about so that you will be able to formulate more interesting questions in your career, right? Your career is going to span another 50 years, the students have, right? Or even the junior faculty. So you want to start it well with a broader setting without any reservations and prejudice about certain disciplines. Okay, so that is about non-relativistic. But the fluid mechanics is a very broad subject. There are branches of fluid mechanics which require relativistic ideas. There are branches of fluid mechanics like quantum fluids, superconductivity. Those things require more discipline from nonlinear Schrodinger operators and more quantum physics type. So these are not far away from the same type of formulations we are talking about. Maybe some of the operators they are occurring there may be different. In my experience as a mathematical scientist growing up in the defense establishment, I am exposed to fluid mechanics in all ranges, and often my publications do not cover, it simply cannot cover, but I can nevertheless tell you about the type of challenges that you encounter in applications, actually fairly broadly based. Okay, so so that's the classical picture. We can understand in the next couple of weeks. And my Coimbatore lectures we centered the whole discussion on general relativity. So that I just put that as a so relativistic. I just leave it as relativistic. So the main equation we studied there is the Einstein field equation. Mind you, I am still waking up, so apologize for not having the full energy, but I think that's the right energy for to have a low-key talk. So the Einstein field equation, we spend a lot of time, takes this form. Gij is equal to some constant. What does that constant look like? 8 pi by c to the power 4. So you guys remember. So you remember better than I do, so then that's I have succeeded. So Okay, so never mind this constant, but this side is what's called Einstein tensor. For the metric, and if you write it out, you get a second order hyperbolic operator, right? So it's a quasi-linear hyperbolic operator. The right, sorry, this is the left side, and the right side is called the energy momentum tensor. So the energy momentum tensor can come from either fluid mechanics or from the electromagnetic field, or at the quantum level, it can be it can be about some spin half direct particles. This is a very rich equation. We won't derive in this lecture because there was another arena where but it only takes about one lecture to derive and understand. But this is rich because it brings fluid mechanics to relativistic speeds. And when the space is curved, and if the curvature is 0, then you have that, and this tensor has this special property called the Bianchi identity. So the Bianchi identity tells you that this is divergence free. So the divergence free condition is expressed as Gij, right? It is equal to 0. So that also means Tij. You are summing over, sum over. And this basically gives you the equation of fluid mechanics. At the relativistic level or non-relativistic level. So that's one way. Another one I didn't say that, okay, I said there are two ways to derive, so there's a third way to derive. So if you are trying to control fluid flow where in situations where the space is curved, close to relativistic speed, then the right equation is Einstein field equation. This side, as I said, is even if you set Gij simply the is equal to 0, this is called Einstein vacuum equation. This is still interesting because it's a quasi-linear second order PDE for the metric tensor for the metric tensor Gij. Metric tensor is the dependent variable there. So that problem is still interesting. So the controller fluid part, or the fluid dynamics part is here. Has anybody thought about controlling at this level? There are some, in fact there are, there is Hollywood movie called Contact. It's, I think the person who wrote the book was Carl Sagan, who wrote a book on Contact, and then they made a movie, I think with Judy Foster and I forgot the actors. And the idea there is to maybe pierce the universe and go to other universes and things like that. But you forget whether you can control the universe or not. In satellite control and so forth, they do deal with relativistic corrections and so forth. So, but and then there is applications like free electron laser. The Navy doesn't want me to come and talk about free electron laser here. So in subjects like that, you do deal with relativistic dynamics. So there are maybe developing control theory for this equation would be more interesting. Yeah.
We also have a gravitational constant G over there, 8 by G.
Here there's a lambda, right?
G.
Yeah. Okay. Yeah. Usually you put it as a lambda or something. You do it so that the first linear approximation you should produce Newtonian mechanics. So that's yeah, gravitational waves. Good. But I think where the G comes, can I just put a lambda and get away? Because I can't remember. Okay, so that's relativistic. This is an open, developing a control theory for this is open. So we can leave that as a theory for for Einstein field equation is open. So if somebody wants to develop work on this subject, this is a very good subject. Why it is I am suggesting it because the rigorous theory of Einstein field equation is been developing this recently. You look at the work of Kleinerman, for example, in Princeton. So the solvability is a very hot subject to look at the solvability of this partial differential equation. And therefore, it's a natural question to ask, never mind what type of application you have in mind. If you are just interested in the mathematics associated with this, and then you want to go into some math department and teach, and maybe 20 years from now you find an application, but enjoy doing good mathematics, take on Einstein field equation. And okay, so that's and thirdly, fluid mechanics also overlaps at the quantum level. So at the quantum, I don't know why I had difficulty spelling today. So did I spell it right? Trust me, the Utpal was very kind enough to get a nice flight, but the first flight was from, actually I had to take a shuttle from Monterey to San Francisco. I discovered that there was a shuttle, they will take you. And then San Francisco to Dubai, it was a 15.5-hour flight. And with, yeah, I won't tell you all the interesting things happened there. And then there was a nice short flight. So I'm still after recovering. So at the quantum physics is a big subject, it's a difficult subject, but for functional analysis, it's far more stimulating to look at the developments in quantum physics than even in fluid mechanics. You don't really immediately find the connection. Quantum physics, the spectrum correspond to quanta and whatnot. So so you do see this one-to-one correspondence between what you study in a function analysis class and in the development. And so the two things the first one is it's called quantum fluids. Actually, that is connected to what's called the Bose condensate. Bose-Einstein condensation is actually governed by nonlinear Schrodinger equation, and probably you will see some of that in Professor Brezniak's talk, because he's going to talk about what Ginsburg, Landau, and things like that. So the quantum fluids is that, and there's also actually a fluid-like characterization. The one more subject along that line is called the Dirac equation. This comes in relativistic electrons. Okay, now so in my recent last several years or even before, when I talk about control of Navier-Stokes, I did also go and think about control of these others with the various reasons. This of course come in superfluid theory, and this comes in some weapons systems. For example, the defense here is interested in such as the free electron lasers and things like that. The equations, you want to accelerate a bunch of electrons at relativistic speeds, and then you want to place magnets, and then whenever you decelerate an electron, that produces electromagnetic radiation, and use that radiation to amplify an existing radiation, and that's what is called the super laser called free electron laser. Usually the lasers tend to be in a certain frequency. Free electron laser you can tune and so forth. So it's a very it's a subject of tremendous interest to not just the US but many countries, governments. And the PDEs is fascinating how this family of PDEs, it's called the Dirac equation, is taken from the square root of the Klein-Gordon equation, deal with, characterize the motion of electrons. Why I picked this desperately, seemingly sort of disconnected subject? They are not mathematically, they are not that disconnected, first of all. They are governed by linear or nonlinear partial differential equations. With linear part maybe parabolic in some applications, hyperbolic in other applications. Applications here in nonlinear Schrodinger equations, in the Dirac equation, in the Einstein field equation, the linear part is hyperbolic, and compressible fluid flows implicit the linear part is hyperbolic, and the compressible viscous flow, the linear part is parabolic. So in some sense that's the most uninteresting situation. So why people first focused on that? Because that's the easiest one to do. When people developed variational methods, when they develop semi-group methods, say the PDE with parabolic linear part is easier to develop, and wave type is harder. It has finite speed of propagations, localization properties, and so forth. And so to me the opportunities are in this broader spectrum of mathematical physics, with of course important engineering applications, where the opportunities are, and then there are PDEs where the equations change type and so forth. Okay, so that's sort of an extended introduction. I have another half an hour, 40 minutes. I can go until what, 10:30? Yeah. Okay, so now let's. So feel free to think about these questions. Although most of these today's discussion and next 2 weeks is going to be what, incompressible viscous flow. But whenever we can, hopefully we can touch some of these, so that control theory. Why should only we control incompressible flow? Is that the only application? Right. That means you're only talking about undersea vehicles, right? Water, the vehicles not even with free surface, and many of the applications are much richer. There is things like combustion, where fluid mechanics actually couples with reaction and diffusion systems. And so that is another example where the phenomenology is coupled. If you notice that I didn't make a big deal out of the MHD, even though that's an interesting, because it's sort of in this already, what I think I already spoke. Okay, so that is to essentially map the territory for now let's talk about, go back to fluid mechanics. No control or no stochastics today. I just want to revisit, for those who already know, it's good to hear it again, because it's this subject is good to understand it, and some of the things we are going to derive is also useful in when we go to Boltzmann and things like that. I want to just derive the fluid equations of fluid mechanics, right? And let's see, this is the way you always studied it. I didn't always study this way, unfortunately. I studied it with all kind of ways. And first, also when you study fluid mechanics in engineering classes, actually they really teach you very well at various stages. You don't see the Navier-Stokes equation first. I never heard of Navier-Stokes equation until maybe third year, and that's junior year. Until then, we first study inviscid flows, so that's more like potential flows. Bernoulli's equation, you think in terms of those, and then you went and take a course go into continuum mechanics. Solid mechanics and fluid mechanics sort of bifurcates, and then we study that way. But these days that's not how we talk about. We just immediately hit Navier-Stokes. It doesn't. It's okay to study that way because we don't have all the time to go through that way. So we will start with, so it's a derivation of equations of classical fluid mechanics. So in Shinbrot, is it so loud that it bothers you? No? In Shinbrot, he first, like I said, he first give a statistical mechanics derivation, which we will look at later. And then he says it's a fluid mechanics derivation. And so that's what we will study. And this derivation, I think, is probably evolved. James Serrin once told me that it's Truesdell who actually cleaned up all the mess that existed in fluid mechanics literature. If you take traditional books in fluid mechanics, there'll be a box and then fluid comes here, fluid goes there. Some of the aspects make sense. The moment you have free boundaries and discontinuities, then you are in very big trouble. So the first thing you want to prove is what is called the transport theorem. So the transport theorem is described like this, pictorially. I have not been using this board, so I will use this one. This is the right pen. Okay, so transport theorem says this is a continuum fluid, no particles here. Even though that would have made a lot more sense, because we first learn about particles and then take many particles. You see birds fly as together. You see, fish sort of moving collectively. You see Coimbatore people, staying moving. So are they governed by equations of fluid mechanics? Right? This, so that it makes a lot of sense in that statistical mechanics derivation, because we first understand particle mechanics very well, right? That's how we even get into universities. You're very good in mechanics, classical mechanics, right? And it is called by different names. In Sri Lanka, it was called the applied math, right? I don't know whether they changed. So we study applied math and pure math. Applied math means is mechanics. And therefore, that would have made a lot of sense, but we will postpone that to the next step. The reason why I picked this example of swarms moving is maybe you may find another application. You go, you get a job in some place where they want you to analyze swarms, and then you think whether is it governed by fluid mechanics. And it's, for example, traffic flow. There's a famous paper by Lytle and Witham in the 50s, deriving the first order hyperbolic PDE for traffic flow, and then explaining that the shock waves you get, like the Invisible-Burgos equation, the traffic jams and so forth. So this idea is not far-fetched. So let's say you have a you want to work in Euclidean 3 space for the moment. Let's write it x1 to, let's say, n-dimensional space. You don't need to worry about so you have an n-dimensional Euclidean space, and let's say you think of a piece of fluid, right? So you have a piece of, you cut out a piece of fluid, right, because you want to understand. So let's call that one, that shape as omega naught. And so fluid movement in the continuum mechanics characterization is you just try to come up with a set of equations, starting from there, prescribing essentially like a, when you begin, it looks like a branch of Poinsett topology or something like that. So essentially you have a domain, and this domain is mapped one-to-one onto to another domain. That domain we call it omega t, right? And so this means that the points here use this coordinate system. What do I do for the next coordinate system? Can I use y, right? So let's call, so these points were x1 to so this is xi. So xi is x1 to xn, and is mapped to a point, let's call it yi. So yi is y1 to yn. So this map, let's call it phi, and it is parameterized by t, and it depends on the initial data, and therefore it's like that. So it is the map is y is equal to phi of x of t, y comma x sin Rn. So that is our fluid motion so far. It's just a map, because that's, after all, end of the day, you know, something that moves like a fluid means maybe a certain region is being mapped to another region, and in a way so that it doesn't leave holes when you map. Of course it can. When you have seen that, you know, when you open the pipe and when you slow down, you will find that now all of a sudden it sort of flows through the end. Or maybe you have there's a famous phenomenon called cavitation in the underwater propellers, where what happens is there's a bubble forms and the water actually peels off, so it forms a free surface. You know that and therefore something that starts with no holes here may end up develop holes here, but we assume that maybe a simply connected domain is mapped to a simply connected domain. What is the condition for such a map, students? 1 to 1. What do you need? That's when you hear about some name. Try something and then, who knows, see, I am still suffering from jet lag, so if you say something wrong, I may what I need is that I want to characterize the notion of fluid flow, right? So I want one point to be mapped to one point and not one mapped to 3 different points, right? And I also don't want one point here came from several points here. That may all happen in different systems, but something that deforms like a continua, as we like to say, like a solid that is bending. Like you know, just take a flower dough and then you massage to take it to another shape. Yeah, so diffeomorphism is very advanced. In some sense, it's advanced notion. So what do you want? You want the locally it's 1 to 1, right? So the Jacobian should be positive, because if the Jacobian changes sign, then you are flipping the map. So you want. Yeah, the on2 is a sort of a global thing. Let's only ask for the local, right? Locally, the transformation to be 1 to 1 is the Jacobian should not be 0 and should be stay in one sign. So that may be, so we want, the condition Jacobian of the map they came late, my 2 friends, and actually one of them is my brother, and they missed all these Nobel Prize ideas I gave out right before, right? So now they are only going to study a little this traditional fluid mechanics. So Jacobian of the map. Well, in one dimension, Jacobian means essentially you are looking at the derivative, right? Multi-dimension Jacobian means it's the determinant. So let's call it J. So it is the determinant of the matrix D yi by this is one. You know, it's a notation like that, or maybe in terms of d phi. This is sort of, if this notation puzzles you write this as determinant of d phi x1 to xn t d phi I over d xj. Right, so essentially you form the matrix of these derivatives, and you want this to be bigger than 0. So you want this condition to start with, to make sense out of what is a fluid mechanical characterization of what we are starting with. So transport theorem, I have given lectures over in Coimbatore and so forth. If I give you, here's a homework assignment, and maybe one student will, out of the 100, will come back with an answer. The other one will say, forget the professor, and let's see what else he got in the next lecture. So, but I'm still going to give you, because I'm sure if you don't do this, you may get it as in the exam question. So in order to prove transport theorem, prove Euler's lemma. Professor Manna knows it because he probably got it for a homework or final or like that when he was studying with me. So prove Euler's lemma, dj by dt is equal to j div. Let me write this way: div of y of u. So I didn't define u yet. Let's write it as u. U, where u yt is equal to d phi by dt xt. So this is so we need to clarify what these things mean. Okay, so maybe in some sense I got too enthusiastic, where I wanted to define the notion of velocity, and then could I have given that, or maybe say there's the reason why I jumped and said we need to first talk about Jacobian is how the Jacobian changes in time is going to be crucial here, and changes according to that law. Okay, so we prove Euler's lemma. We will leave it is, and we will come back to this in a moment. So we need to talk about the notion of velocity, and so the velocity. So it's only one color chalk here. So it's okay. Actually, these same concepts you actually also study if you start studying first order hyperbolic systems. You study the same concepts again, and but you make it comes with a different notion. So you want to talk about the velocity. What is meant by velocity of the fluid, right? So what is meant by velocity? How fast this thing is moving, and so in order to do that, so we want to say, I want to ask the question that here, if we are here, what is the velocity? What do you mean by velocity here of the fluid, right? So that so you denote by velocity of the fluid and they use the word particle here. There is no particles. This is not a particle mechanics, but in the continuum fluid mechanics also they use the notion of particle here. But it's just a convenient way of saying it. The real particle thing will come later on. So we just want to say at this point, how do you characterize velocity? So you say the velocity u at a point I am putting t or y on the first side. I am putting t, x. Okay, is correct. I want to say whether I am using t, y or yt. So we want to define this one. How can you define the velocity? A candidate. So I will say I will take a look at this map. And this map, what does this map tell you? First of all, phi tells you the phi where you are. You are on point y. And the t signifies how long we are characterizing this whole dynamics. What does x characterize? Yeah, I don't want to keep picking on Coimbatore here, but that tells you where did you start, right? Because it tells you it started here, right? So x tells you where you started, and t tells you how long it took to get here. And I want to define the speed u at this point by fixing where you started. So in this way I am talking about the speed of those particular points, right? And so, and that's why we write it as d phi by dt x t. So notice that the x is x and y are connected here, right? Are they connected? Yeah, because I have an x on the right hand side and I have a y on the left hand side. Are they connected? Yeah, they are connected by where y is equal to phi of xt. This relationship is important. In fluid mechanics books, they will also simply go and write this one as dy by dt, right? So that's a notation we will postpone a little bit because it's a little bit, but it is dy by dt. If you look at this side, if you fix this one. So in hyperbolic system, first order thing, you often talk about the equations of characteristics. So along a characteristics, here we also essentially building the characteristics. Along the characteristics, starting from the point x. So we say we want to fix x. We only want to talk about that particle which started with here or that point, and we define the notion of. So that's why here in the Euler's lemma, we had to say this is a function of the right hand side. So the j is a function of j at this point is actually a function of x and t. You can actually regard this as a function of the initial point and t. Right? Is correct? So by dj by dt, I essentially means that I am going to fix this little x, because otherwise you are going to have too many things that are varying. We just fix x where we started, and so when I write dj by dt, I mean that whatever the mess I have here, I am going to fix my initial position, and I am going to differentiate with respect to time. So that variation is equal to the Jacobian times divergence computed in the y variable, right? So this is also again important. What is this means? This divergence is du1 by dy1, dun by dyn. Okay, so understand the Euler's lemma in the correct setting so that you won't get confused by whether it's divergence in x or divergence in y. The whole notion is to somehow describe the dynamics at the point you want, but in relationship to where you start from here. Okay, so once you know, so you can see that all you need to do is to prove this, is to write down the Jacobian, right, matrix, differentiate it, and use your understanding in cofactors. You are more close to cofactors than I am. You studied it recently. I studied it 1,000 years ago. So, and then you will find that you simply differentiate the expression. Use the fact that your velocity is defined by fixing x. So the ith component is ith component here. You could have written dy by dt, but dy by dt is not very telling. It is better to think that is a map. So this comes in, if you look at Homanda's book on lectures in hyperbolic, nonlinear hyperbolic PDEs, he does it somewhere in the first few pages because it's very crucial, even though he appears not to talk about fluid mechanics. If you start either Shin-Brott or Boltzmann equation, the transport as well as the Euler's lemma is in there. That's the start of understanding the transport theorem. Okay, so now having given that as a exercise, maybe the tutorial is a good thing to go through. But and the the Puneim, Eliim, I want to speak in Tamil. I don't know. I forgot that I'm this part of the world don't understand the cat and mouse game. Where your solution was offered that because this cat has been rampaging the rat population. So the rats got together, had a committee meeting, and said that how to deal with this. So somebody suggested that why don't you tie a bell on cat's neck, so that when the guy comes, he would know. Then the question is, but then who should go and tie it? So this is my. I nearly told that story in Tamil because we want to have a tutorial session on that one, but before that we had to learn to derive it. Anyway, so postponing that, let's go to the derivation of the transport theorem. So you are with me so much, right? Interestingly, transport theorem is also, in some sense, one of the starting points in the prelude to the Boltzmann equation characterization. So it's useful to correctly understand. If you math students, of course, you study, points of topology and so forth. So already I am taking derivatives and talking about one-to-one maps and all that, and there are a lot of rigorous theorems, a question mark whether it is such Jacobian will stay positive for all time, and all these very mathematical questions already in there for fluid mechanics. Okay, so the transport theorem is again centered around this one. If you are already say that okay, you can handle what happened so far. So now you say that you go to a domain like this and say suppose you have some function some function which is when you are here in fluid mechanics, when you have a thermostat measuring the temperature or something where you measure the velocity of the, let's say, fluid passing through some speedometer or something like that. I don't know what instruments they use. Measuring the velocity. It's very inconvenient to say it's gauging of the velocity based on the previous position, right? Everything has to be brought to here, where you are instrumenting. And that's why I'm trying to bring all the attention to this domain rather than that, but not forgetting where I came from, right? So, but we are going to have, the entire fluid mechanics, and along with many other mechanics we can talk about functions and vector fields which are defined in these variables in this location, right? So we are interested in a function called f of y of t. This function can be can be a vector or a tensor. It's okay. Okay, so and then I want to integrate in the y variable, right? So this is Euclidean spaces. I can write dy. I don't need a measure. In fact, there are stories similar thing carries. And then I am interested in the integral of that in this domain. So notice that this is very is an attempt to somehow bring the attention to any point you pick. And you want to characterize the velocity or temperature field or magnetic field at a point y in a and you want to know the average of this in this variable domain. And yeah,
because you're integrating omega-T, right? It's a kind of a surface of manifold.
it's a domain. Yeah, right.
So the dy is the Lebesgue measure, right?
Yeah. So whether it's defined, you mean?
Lebesgue measure on Rn or in the surface?
No, it's Lebesgue measure in the interior. So it's just the Lebesgue measure in because I am integrating not on the surface, but not just the volume integral, right? It's a volume integral. So this omega t signifies the domain. If you want the boundary, we call it d omega t. Okay. So this looks like a very reasonable question to ask. How to characterize this and how it changes with time. So, can you take the d by dt inside?
If you fix the domain, we can take it.
Yeah, but I am not, it's moving. It's a function of time. Let's say it's in one dimension. We don't have to go to a million dimension. I have one dimensional integration, right? From A to B or something. A is a function of time, B is a function of time. How do you differentiate? Can you take it inside? You will go to hospital if you do that. That's what is called. Is that right? No, it's not hospital. L'Hopitas is the Leibniz rule. Yeah, not hospital. I'll send you to later. I was thinking about L'Hopitas. I'm still recovering from. Why don't we recall the L'Hopitas rule? The Leibniz rule. Can you help me recall the Leibniz rule since I don't remember? So first you take it inside, right? So it is when you go inside, notice that when it's outside, there is a y integration is being carried out, so you only a function of time. When it goes inside, it becomes a partial derivative, right? So it is df by dt, t of y, dy, and then? So what is that?
It's Leibniz rule.
F of?
D comma B of t. D comma B of t. D by D, B dash of t. dB by dt.
Times b dash t, right? Minus
F of t comma A of
f of t of at. So this is the so the Leibniz rule. So something similar to the Leibniz rule we look for in the multi-dimension, right? How could you say that when you go to a multi-dimension now there is no, I take d by dt inside. So there is, so the Leibniz rule we want to come up with is what is called the transport theorem. So just that this is being combined into something inside, okay? So let's do that in an organized way. One student correctly said that yes, you need a fixed domain. So what we will do is, we go back to this domain. So that's why we need this map, right? We need to, we don't, even though we have, this is perfectly normal, at the time fixed, time t, you can execute this integration like the way you usually execute the integration, right? But just that now you want to take this time derivative or parameter derivative, so this guy is varying just like in the Leibniz rule case. So you want to take it inside. So what we do is we map that whole integral, go back here where you came from, right? So you keep the d by dt. The integral is in omega naught. So the if now, well, this guy inside, if it's a tensor, you need to do a little bit more work. Yep.
Time t fixing.
Say it again.
Sir, here we are fixing our timer.
This much you are fixing the time, right? Here you are fixing the time, but when you try to take time derivative, you are evaluating at a certain time and evaluating another time and differentiating, right? So when you execute this derivative, you know, let's say you somehow solve this one and got, let's say, sine t after integration, then it's just a differentiation of that, right? Because once you finish this one, you are only a function of time. But the difficulty is that the integrand, the derivative of the integrand itself won't give you the variation, because the domain of integration is changing, just like the Leibniz rule, right? Okay, so how do you map this to, I want to map it, give this one a little bit more respect. So let's do it here. So you write this as d by dt, and so you want to write it in omega naught. So here now you still have the same function, but now we want to carry out our integration in the x coordinate, right? And therefore y is now interpreted as a function of x, that you had to give meaning to that. So it's better to go and write the phi if you want, right? If you leave y, then you are going to have this, so it is phi of x of t. So this becomes all of a sudden very rich and interesting, right? Times what happens to the integration dy. Yeah, even in one dimension, if you want to make the variable dx, it is dy by dx times dx, right? But this is a multi-dimension, right? And therefore Jacobian. It's the same Jacobian we already looked at, right? Dy by, so it is Jacobian, right? Then Jacobian is also, remember, it is going to be, you know, I need to be careful about the history and so forth, right? So if you want, you can leave it as a function of x and t times dx now, right? It is dx here, by which we mean dx1, dxn. Be careful talking to engineers. A friend of mine recently lost his grant because he spoke, and the reviewers were unfortunately engineers. And he had dx there, and they asked, why are you only integrating in one direction? And the whole 1 hour went on trying to tell them that it is. No, it is d1, x1, because they, okay. So agree that so far all I did was I took this integral, I wrote it in the coordinate system where this domain came from, or this particle came from, right? Now we can go inside and differentiate. And also we wrote it in a way so that we know when you take derivative what to do. Okay, so when you differentiate, now you can take it inside. I don't need Leibniz rule now. Why? Because the omega naught is fixed, right? I go back. So when I differentiate, what happens? I have two terms here to differentiate to begin with. Even this guy, I need to do a partial differentiation. Do you agree? Right? So if I take it inside, I have this is equal to omega naught. First fix this guy, right? Fix and differentiate. So it is df by dt. Make sure that you know what you are fixing. What are you fixing when you do that? You are fixing little x, or you are fixing y? How many for x? How many for y? Y, because you are fixing the whole thing, and therefore you are fixing y, right? I know that you will have difficulty here, that's why I took you through. Been thinking about fluid mechanics for 40 years now. So, what I do, because we are trying to do a partial differentiation, the whole thing is y, right? So you want to fix y, differentiate this. And then we differentiate with respect to phi or y, right? Little x will come, we will see. So, yeah, so first you do that, and then second one, it is df by dy times, let's write the dy by dt this side, okay, because it's a vector, df by dy times differentiating this with respect to time, fixing little x. What is that called? We gave a name for that. Say it again, louder. U, that's the velocity, remember? So this one, if you differentiate this one, fixing where you came from, that is your velocity. So that gives you u here, right? U as a function of y and t. So that times j, that was the first term here, agreed? So that's keep that, plus then f times dj by, right, dj by dt, fixing little x, right? So whether I put d by e or partial doesn't matter, you just make sure which you are fixing. So what is dj by dt? So that is j times div with respect to y of u, correct? Times dx. So this step is most crucial step in fluid mechanics. If you struggle with little x, which to fix, which to write, get this one straight. All we did is we want to take it inside, differentiate with respect to time. So when we so it says the first step is okay, I am going to fix this one, differentiate this. That is this term. Next time I am going to do a partial differentiation with respect to y. So that's the differentiation with respect to y, and then you differentiate with respect to time, fixing little x, and we took the liberty to define that as our velocity at point y. So, okay, so that is the derivative. So that is equal to, now I can, I took the liberty to write Euler's lemma, use the Euler's lemma dj by dt, or you could say dj by dt, fixing t, fixing x is equal to j div of y of u. I use this one here. Now gather the j's, so that will look like omega naught df by dt plus, I combine these two, this j is gone out, I combine these two as divergence of y of f and u times j dx. Now I can go back to my original the y coordinate system, right, because I want to express everything in the y coordinate system. This moving back and forth between the coordinate system you started with and the one you would like to pay attention to, bring is also very useful in understanding free surface flows and so forth. So and therefore d by dy, so the transport theorem, omega t, so notice that now I can go back to my original coordinate system because I recovered this guy, right, j d by dx in omega naught, and therefore I just simply go and write it everything in the y coordinate system. So it is equal to f of yt dy is equal to omega t again of df by dt plus divergence in y of f of u. What is this? This is not a dot product here. This is a scalar and this is u. If both of them are vectors, then it will become a tensor product. This calculation goes through because I can just go and put an index to I times dy. From this you essentially all the equations of fluid mechanics follow. This is called the fluid mechanical derivation. I haven't finished the derivation yet. Everybody agreed? Okay, so this is the transport theorem. Okay, so the first equation we will derive before the break is the equation of continuity. So I have the transport theorem. All I wanted to do is how these time depend. Like I said, transport theorem is nothing but a multidimensional version of the Leibniz formula you know in one dimension. Question? Question? No, you have a question. Asking something. Okay. Because every time they discuss and I'll say, is there a question? They'll say, no, no, we will go and figure it out ourselves or something like that. Okay, so so the first one is called the equation of continuity. So the equation of continuity is that suppose you have a quantity, a scalar quantity, which is like this f. So let's say rho of yt. Unfortunately, I cannot use little x. Little x we reserved it for this original point. Later on, we will. So let's say it is the density. Density. So if I integrate omega x t, of yt dy, it essentially tells you the total mass inside this of this bulk of fluid. It could be total mass, or it could be if it is not fluid mechanics you are talking about, it could be, I don't know, some mosquito population, or these ideas have been used in other areas. So it's so you are interested in, so this is like the total mass. So you are interested in how the mass is changing, right? What is this equal to? Why it is 0?
Conserved
Why
fluid.
it is conserved?
Either created
Destroy
or
mass.
either created or destroyed.
Why the sweat vaporizes? Or maybe some, right? Or if you have some droplets, they evaporate, right? So.
Sir, we are connecting, we are taking that omega t is simply general domain.
Yeah.
So there will be no source or sink.
No, it has nothing to do with source or sink.
So it's easy.
No. It can be simply connected. This room simply connected. Yeah. And why water evaporates? So it has nothing to do with that. So there may be some source or sink in the right, producing creating this rate of change of mass, total change. So that you can have. There are many examples of. Since my time is up, I will come and finish. But I want to tell you an example because this is what came to mind. How many of you have heard about Yellowstone National Park? The Yellowstone, he knows because in Wyoming and also Montana, that area is called Yellowstone National Park. It's actually a super volcano, but now it's not. The last time it went off was 650,000 years ago. Apparently, it goes off every 600,000 years ago. So it's sort of. But if you go to Yellowstone, you will find that these is called geysers, right? These are from the ground. You will see this ejection of steam to the air, or maybe you will also see ponds which are boiling, and it's almost like the beginning of the world. I don't know, for some reason I was thinking about yellow stoneware. You can have most of the applications you are going to encounter. You will have sources and sinks, which will actually create this rate of change of mass. But in its simplest setting, if you set it to 0, then that will give you an equation of continuity. If you don't set it to 0, set it to a source, which will come back and do that. It gives you a slight modification, but ready to think ready to think about situations which are somewhat real world, and you will find that the mathematics is very elegant. Okay, so we'll see after the break.